Welcome friends, welcome back to NPTEL online certification course entitled Soil and Water Conservation Engineering. I am Rajendra Singh, Professor in Agricultural and Food Engineering Department, IIT Kharagpur. We are in week number 2, this is lecture number 9, and the topic today is modifications in universal soil loss equation part 2. That simply means that it is a continuation of previous lecture. In the previous lecture also we saw modifications in universal soil loss equation, that was part 1, and today we continue onwards, go to part 2. Just to give you an idea about the course content for this week, once again in lecture 6 we started with the soil loss estimation, and there we saw the use of the one of the most popular equations known as universal soil loss equation for estimating the soil loss. Lecture 7 we spent on determining two important components of universal soil loss equation, that is erosivity and erodibility. And in lecture 8 we saw that universal soil loss equation has been modified to modified universal soil loss equation. And just to remind you, in modification is that rainfall erosivity index or rainfall erosivity factor, which is a part of universal soil loss equation, that is replaced by a runoff factor. And in the runoff factor there are two unknowns, that is VQ, which is surface runoff volume, which is normally determined using SCS curve number. And in lecture 8 in part 1 we covered that modification in universal soil loss equation. The second unknown is QP or peak rate of runoff, and in today's lecture, lecture 9, we will go through the modifications universal soil loss equation part 2, and we will start with the how to find QP, and then we will further go ahead. And in last lecture of this week, we will cover soil loss measurements. So, let us begin with today's lecture. Just to give you once again an idea about the modified form of universal soil loss equation. So, the modified form of universal soil loss equation is given by Williams in 1975, and it is given by the following equation: A equals to 11.8 VQ times QP to the power 0.56 and KLSCP. And you remember the universal soil loss equation original form is A equals to RKLSCP. So, basically this R, which is the rainfall erosivity index, that is replaced by a runoff factor here. And here just now I mentioned that VQ is volume of runoff, and this runoff volume is estimated using the SCS curve number method, and the other unknown is QP, that is peak flow, which is estimated using rational method. So, rational method, let us start with rational method. It is proposed by Mulovani, an Irish engineer way back in 1851, and this is given by this relationship Q equals to CIA by 36, where Q is the peak runoff rate in cubic meter per second or cubic. C is a dimensionless runoff coefficient, I is the average rainfall intensity for a duration equal to the time of concentration and a desired frequency or return period, and the unit used is centimeter per hour, and A is the catchment area in hectares. So, once again because we are using this CIA by 36, and like any empirical equation, if we have to use this constant 36, then we must always remember that unit of I is in centimeter per hour and unit of A is in that is catchment area is in hectares, that is we have to remember. And like while discussing about the universal soil loss equation few lectures back, I told you that there are certain things as a student you are always expected to remember. And rational formula is one such thing, that if you have read hydrology, if you say that you are an agricultural engineer, then it is expected that you will always remember rational formula along with its variables. So, just to repeat you, rational formula is Q equals to CIA by 36, where Q is the peak rate of runoff in cubic meter per second or Qmex. C is runoff coefficient. I definition of I is little tricky. So, you must remember that is a average rainfall intensity in centimeter per hour, but it is defined for a duration equal to time of concentration and a desired frequency of return period. So, these two qualifiers are very important while defining I for in case of rational formula, and A is catchment area in hectares. So, this is rational formula is all about. Now, there are certain assumptions of rational formula, and these are the assumptions of rational formula, that is rainfall is uniformly distributed over the catchment. Second assumption is rainfall is uniformly distributed over the storm duration. The third assumption reads that rainfall rate resulting from any rainfall event is maximum when the rainfall lasts for a duration equal to or greater than the time of concentration. The fourth assumption says that the return period of peak runoff is the same as that of rainfall intensity, and the last one says that the fraction of rainfall that becomes runoff is independent of rainfall intensity or volume. Let us take these assumptions one by one, and basically as you can see here, the first one says that whatever be the area of your catchment, rainfall is assumed to be uniform throughout. So, be it a area of 10 hectares or 10 square kilometers, the assumption says that rainfall is uniformly distributed over the entire catchment. Second is about the storm duration. Again, the assumption says that if a storm duration could be of 1 hour or 5 hour duration, but rainfall intensity remains, it is assumption that rainfall intensity remains uniform over the entire duration. The third one is the basic reason behind the definition of intensity of rainfall. You remember we defined rainfall intensity is in rational formula as average rainfall intensity having a duration equal to time of concentration, and that comes because of the assumption that it is assumed that the runoff rate will be maximum when the rainfall lasts for duration equal to or greater than the time of concentration. So, if a rainfall event occurs for a duration equal to time of concentration or longer duration, then the runoff rate will be maximum, that is the peak rate of runoff will be generated. And the next one is that the return period of peak runoff is same as that of, that is there is a equivalence between the rainfall and runoff, that is the assumption. So, these are the assumptions, and as you can very well imagine, if we just concentrate on the first two, we know that there is hardly any rainfall, or rather in other words, we see many rainfall events where it rains at one part of the area, town, campus, whatever you call, and it does not rain next door, maybe 500 meters away, you will find that there is no rain. So, it is very hardly it is difficult to get a rainfall event where the rainfall is uniformly distributed over the entire area of interest. Same is true with the distribution of rainfall over the storm duration. We know that in any given rainfall event, the intensity of rainfall goes up and down. It rains very heavily for some duration, then it becomes milder, and then it might become very heavy. So, hardly there is any rainfall event where the rainfall is uniformly distributed over the storm duration. So, these are the assumptions which bring a question mark to rational method, but practically it is seen that it gives a pretty good estimation of peak rate of runoff, and that is why it is quite popularly used in spite of these limitations as far as the assumptions are concerned. Now, for estimation of peak runoff using rational method, these are the steps we need to follow. That is, we have to choose the runoff coefficient C for the watershed. We have to estimate the time of concentration T c. We have to select a frequency of return period for defining the rainfall intensity. We have to obtain the intensity duration frequency curve or IDF curve for the region. Then we have to determine the average rainfall intensity from IDF curve, which is I in the CIA by 36, and then finally use the rational formula to estimate Q QP or peak rate of runoff. So, these are the steps we need to follow. Let us see one by one how to do these or take these steps. So, first thing is runoff coefficient C, which basically represents the fraction of runoff to rainfall, that is a part of rainfall gets converted into runoff, that is represented by C, and basically it represents integrated effects of infiltration, storage, evaporation, natural tension and interception. So, a lot many abstractions which we consider in hydrological cycle. Before when rainfall occurs, there are certain abstractions before rainfall gets converted into runoff. So, the integrated effect of all those abstractions are represented by this runoff coefficient C. And as you can imagine, because each of these processes are quite complex, it is very difficult to determine the precise value of C, and so that designer must use his or her experience and judgment in choosing its value. So, it is a little subjective matter. And there are standard tables available for obtaining the value of C runoff coefficient, and for that the drainage area is divided into urban area and agricultural area, and then various kinds of uses are here, and then the value of C is recommended accordingly. For example, if you see streets which is supposed to be quite impervious in nature, that means that means no absorption of rainfall takes place there, and the value of C is 0.7 to 0.95. This means that because absorption is less, almost 70 to 95% of the rainfall gets converted into runoff. Then if you look at the agricultural area, say flat agricultural area, and if you look at the sandy loam soil which is cultivated, the value of C is 0.2. That simply means that only 20% of rainfall is getting converted into runoff. So, depending upon whether we are in urban area or agriculture area, depending upon various kinds of uses, the value of C can be read, and also there is a range. So, that is where the experience of the modeler or user comes into picture. Now, many times when we work in a catchment, there is various types of land uses are possible. Like we saw in the case of when we were discussing SCS curve number, then also we saw that because of the land use changes, curve number changes, and then we have to use the weighted curve number. Same concept is used here, that we have to use weighted runoff coefficient. That means, in a given area, if land suppose there are different land uses over two land areas. So, obviously, for corresponding to these land uses, we have to get the value of runoff coefficient from table, and then we have to get the weighted runoff coefficient for the area by first multiplying the corresponding values of C and A, summing up for all land uses, that will be the numerator, and denominator will be the total area of the catchment under consideration. So, this is how the weighted runoff coefficient is obtained. The next important thing is time of concentration we have to find. So, in rational method, TC or time of concentration is used to determine rainfall intensity, because remember we define I for a duration equal to time of concentration, and time of concentration is defined as the time required for water to flow from the hydraulically most remote point of the basin to the outlet. So, that means for defining TC, for finding out the TC, we first have to find out hydraulically the most remote point in the watershed, and obviously it depends on the shape of the watershed also. So, if it could be a fan shaped watershed, it could be elongated shaped watershed. So, depending upon that, if it is elongated, then obviously it will be longitudinally placed with respect to outlet, wherein if it is a fan shaped, then it may be little down either on left or right, depending upon the fan shape basically. So, here basically the time of concentration means that time required for a drop of water to travel following the stream path to the outlet. So, that time is defined as the time of concentration. And typically time of concentration is estimated using a formula, famous formula known as Kirchhoff formula, which was given by Kirchhoff in 1940, and as per this formula T c is equal to 0.0195 L to the power 0.77 S to the power minus 0.385, where time of concentration T c is in minutes, L is the maximum flow length measured along the drainage line. Just now we saw how L is found out in meters, and S is basin slope. So, that simply means that in order to use the Kirchhoff formula, we should know the maximum flow length and the basin slope. These two components we have to know, and then we can use Kirchhoff formula to find the time of concentration. And then also associated is that because I is defined for time equal to time of concentration and for a given frequency. So, that means we have to also decide on a frequency or return period, which is also referred to as recurrence interval, return period or recurrence interval. And choice of frequency or return period basically depends on the nature of project, how risky the structure we are going to design, and standard tables are available for referring these values. For example, we can see this table where guidelines for selection of return period is the title. So, obviously, depending upon the structure, say for example, if you are having a simple road drainage, then the return period could be 25 to 50 years, wherein if it is a serious structure we are going to design. For example, if you are going to design an emergency spillway for a dam where the risk to life of people is too high, then we take 100 to 10,000 years return period, and PMP means probable maximum precipitation. So, depends on what kind of structure we are designing, based on that recurrence interval or return period is chosen. Then once the duration, rainfall duration T c, that is time of concentration, and frequency, that is rainfall duration and frequency are obtained, then we can find the rainfall intensity, and for that we use the rainfall duration frequency curve, intensity duration frequency curve, or IDF curve, which is popularly known, which basically relates I, that is rainfall intensity in millimeter per hour, to storm duration T in hours. So, here this I is plotted against T for different return periods. So, for example, if our T of interest is say 3 hours somewhere here, and our T value is 50. So, obviously, we can find out using this relationship what is the intensity in which we are interested, or intensity for duration equal to time of concentration and of desired frequency. So, this is how we use IDF curve to find out the intensity duration frequency curve. And once everything is decided, then we have to simply use the rational formula. So, let us take a problem and see how to solve using rational formula. So, the problem states that a catchment has a total area of 5 square kilometers and slope of land is 0.006, maximum length of travel is 1.95 kilometers, and a principal spillway has to be designed to handle a flow having 25-year return period. The maximum depth of rainfall in the catchment with 25-year return period is given below. That means, intensity, duration, frequency characteristics are tabulated here, that is for different durations. The depth of rainfall for 25-year return period is given here. Consider that 2 square kilometer area has a cultivated sandy loam and 3 square kilometer has cultivated tight clay. Estimate the peak flow rate for design the spillway. So, almost all data or information is given, and we have to design you find the peak flow rate using the rational formula. So, coming to solution, we have been given drainage area A. Remember, we have to finally use the equation C I A by 36. This is the formula we have to use. So, area is given 5 square kilometers, but remember the unit here is hectares. So, we have to obviously convert. slope is given at 0.006, length of travel is given in 1.95 or 1950 meters, and return period is given at 25 years. Remember, in 5 square kilometers of total catchment area, we have 2 land uses, 2 square kilometer of cultivated sandy loam and 3 square kilometers of cultivated tight clay. So, obviously, we have to read the runoff coefficient table, and we find that for cultivated tight clay the value is 0.5 and cultivated sandy loam the value is 0.2. So, obviously, the corresponding value we have obtained for both kind of land uses. So, weighted runoff coefficient we can find out by first pre-multiplying the area and the C and then summing up, that is 2 into 0.2 plus 3 into 0.5 divided by the total area. So, based on that our weighted runoff coefficient value comes out to be 0.38. Then obviously, we have to use the Kirpich formula for obtaining the time of concentration. So, T c is given by this relationship. We already know the values of L and S. So, putting the values of L and S, we get T c equals to 47.7 minutes. And for 25-year return period, we have to interpolate the table data. So, if we really want to go back to our table, then we have to obtain the values. So, obviously, from this 47.7 minute duration, we have to get the value of maximum depth of rainfall, which will come out to be 62.31 millimeters, and then rainfall intensity we have to calculate, which comes out to be 78.38 millimeter per hour or 7.838 centimeter per hour. So, I is known to us, C already we have found out, A is already given. So, using CIA by 36, that is using the formula Q equals to CIA by 36, by putting the values, I we have to use in centimeter per hour, A we have to use in hectares. So, that is why 5 square kilometers is multiplied by 100 and then divided by 36, we get the value which comes out to be 41.37 cubic meter per second. That is the peak flow rate that we have obtained using the rational formula. Let us take another problem to see how to once again use the rational method. So, an agriculture area has a runoff coefficient of 0.2 and area of 0.75 square kilometers. The slope of catchment is 0.5%, maximum length of travel of water is 1 kilometer. The maximum depth of rainfall with 50-year return period is given here, that is for different durations. The depth of rainfall is given. If the bund is to be designed for drainage at a outlet for this area for a return period of 50 years, estimate the peak flow rate, that is the problem. So, coming to solution, the value of C is given, drainage area is given, slope is given, maximum length of travel is given, return period of 50 years is given. So, obviously, we can use Kirpich formula to obtain the time of concentration. So, putting the values in Kirpich formula, we get a value of 30.6 minutes, and then again given the 50-year return period table data, we have to interpolate the value corresponding to 30.6 meters, and which if we do, then maximum depth of rainfall for 30.6 minute duration we obtain 53.42 millimeters, and that means the rainfall intensity we have to convert for hour. This is only for 30.6 minutes. So, then we get the rainfall intensity is 104.75 millimeter per hour or 10.475 centimeter per hour. So, that is the intensity, and then we can use rational formula Q CIA equals to 36, C value is already given 0.2 here. Rainfall intensity in centimeter per hour we have obtained 10.475, and area drainage area has to be used in square hectares. So, we have 0.75 square kilometers. So, 0.75 multiplied by 100 and then divided by 36, we get a total peak flow rate of 4.6 cubic meter per second or QMX. So, that is what our intent was, that we need to estimate the peak flow rate using the rational method, and that is how we saw the rational method and its application in estimating the peak flow rate. Now, we can take a problem straight away on modified universal soil loss equation, because now we know how to determine various component parameters or variables. So, the problem is determine the sediment yield from a storm with a total runoff volume of 120 cubic meters and a peak discharge of 5 cubic meter per second. Use K equals to 0.33, LS equal to 0.697, C equals to 0.04 and P equals to 0.5. And Mosley or modified universal soil loss equation A is given by this formula. So, almost all variables are already values are straight away given here. So, first thing we can determine is this component. So, Vk Qp to the power 0.6. So, one value of Vq is 120, Qp is 5 already given. So, using this we get the value component value of 35.96, and then we can put the values together in equation. A equals to 11.8, 35.96, that is the value which we have obtained for Vq Qp to the power 0.6, K LS Cp, value of K LS C and P are straight away given. So, using this relationship we can get the soil loss is 1.95 megagrams or tons. So, that is how we can use the modified universal soil loss equation once we know all the variables or the components of the equation. There is one more variation of universal soil loss equation is available, and that is referred to as revised universal soil loss equation. So, this is the third one. We had universal soil loss equation, we had modified universal soil loss equation, and now we have revised universal soil loss equation, which was proposed by Renard and others in 1991. So, basically revised USLE is a cooperative effort between scientists and users to update USLE. So, USLE has been updated, and we will see what are the various new things that has been brought into this updated version, which is referred to as revised USLE or RUSLE. So, we saw USLE, MUSLE, and now we have RUSLE. The most important thing change is that RUSLE is implemented using a computer program with inbuilt database, which is more suitable for application into the USA. So, basically there is a computer program now and there is a database, but only probably limitation is that this database has been generated primarily for United States of America. So, that is the only limitation, but good thing is that all computations can be done using a computer program. And the changes offered in the RUSLE are obviously computerizing the algorithm to assist the calculation. So, user does not have to bother. Then R factor were developed using rainfall databases from across US. So, all the database that was available across the US that have been used for getting the R factor value, and that simply means that new iso-erodent maps have been generated and used. And just for your reminding you, iso-erodents are the lines joining the places of equal erosivity. So, equal erosivity maps have been generated and used in case of RUSLE. And obviously, next change is that a seasonally variable soil erodibility term K, which includes for all soils found in the web soil survey, has been developed. That is, now K has been developed for all kinds of soils, number one, and number two, because from one season to other the crop types could change. So, soil erodibility or the soil characteristics could be affected. So, seasonally variable soil erodibility term has been generated for use in case of RUSLE. And just to give an idea, this is the iso-erodent map example, and this one, the older one, was used by Wismir in 1965, and new one is developed by EPA, that is Environmental Protection Agency, in 2001. And if you just zoom in the same, that is Gulf of Mexico area, so you can see here the isoirradiant maps or the values are much finer, and highest value has gone even up to 700 as compared to the 600 that was the limit in case of earlier maps. So, much finer value of erosivity index can be obtained using the new isoirradiant maps. And other changes are the new slope length and steepness algorithm reflecting real to interval erosion has been incorporated. This LS factor may include multiple slope segment calculations, that is slope could change, and it also allows for depositional feature. In case of USLE, we were not allowing any kind of soil deposition, but here RUSLE allows deposition also. And there is a new approach for calculating the crop management term CE with sub factors representing prior land use, crop canopy, surface cover and surface runoff. So, that means much better value of C is now available, and also there is a new conservation practice value P for rangelands, steep crop rotation, contour factor values and subsurface drainage. So, that means new conservation practices have been also incorporated in revised universal soil loss equation. But the issue is that even though it offers several modification USLE aimed at better estimation of soil loss, it is not so popular because of the simple reason, not very popular because of simple reason that the inbuilt database in the computer program is US centric, which limits its application in other regions of the world. So, there are several modifications done in RUSLE, but its application has remained limited to United States because the database which is inbuilt in the program, that is more US centric. So, this is one of the major limitations, that is why revised simplex method, revised universal soil loss equation is not very popular. And with this we come to the end of this class. So, we really saw how to use rational method for estimating QP, peak rate of runoff for use in the modified universal soil loss equation, and then we saw the application of rational method as well as modified universal soil loss equation. And then finally, we saw the latest revision, that is revised universal soil loss equation. So, all three versions we have covered in last 3 lectures or so. Thank you very much.